Okay, hypothesis testing for the mean. Again, this is when the standard deviation is known. And usually that's not the case, but when it is known, we do a z-test. Otherwise, in the next lesson, you're going to know it's an unknown, so we do what's called a t-test. But everything's the same in both of them, so it just depends on which table we're going to use. So hypothesis testing for when the standard deviation is known. So the z-test score for the mean mu. It's a statistical test for a population mean. The test statistic is our sample mean. So whatever our sample mean is, then we use this formula. Does this look familiar? We've been doing this for several months now. So the sample mean minus the population mean divided by the population standard deviation over the square root of n. Okay, and then as long as these conditions are met, so the sample is random, and at least one of these is true. The population is normally distributed, or your sample size is greater than or equal to 30. Okay, and remember, that's just our standard error of the mean. So it's the standard deviation divided by the square root of your sample size. Okay, so guidelines for using p-values for a z-test for a mean, again, when the standard deviation is known. So verifying words always say that you see that they give you the population standard deviation. In the next lesson, we won't know that, so they'll give us the sample standard deviation. So always verify that you recognize that, and the sample is random, and either the population is normally distributed or state that the sample size is greater than or equal to 30. State the claim both mathematically and in words, what the null and alternative hypotheses are. Okay, remember the null is always the one that has the equals part to it, whether it's equal to or less than or equal to or greater than or equal to. And specify your level of significance by identifying whether it's 5% or 1% or 10% or whatever they're asking right there. Find the standardized test statistics. So that's this z-score formula that we're going to use over and over and over again. Find the area, which is our table 4 of your standardized z-score tables that corresponds to z, okay, and then find the p-value, okay, that's our area. So for a left-tailed test, the p is the area in the left. For a right-tailed test, the p is the area in the right. For a two-tailed test, the p is twice the area that we look up in our z-score table. So make a decision to reject or fail to reject the null hypothesis. So if p is less than our theta, which is our standardized test statistics, then we reject HO or reject the null. Otherwise, we fail to reject. And then always interpret the decision in the context of your problem. Okay, so here's an example. So in an auto racing, a pit stop is where a racing vehicle stops for new tires, fuel, repairs, and other mechanical adjustments. So the efficiency of a pit crew that makes these adjustments can affect the outcome of a race. You guys have seen those guys, they're fast. So a pit crew claims that its mean pit stop time for 4 new tires and fuel is less than 13 seconds. So a random sample of 32, there's n. Pit stops times has a sample mean of 12.9. So there's our x bar. Assume the population standard deviation. Okay, right here, assume the population standard deviation. That says z-test right there is 0.19 seconds. Is there enough evidence to support the claim at the 1% level? And so we're going to use the p-value. So here we go. So the claim is the mean pit stop time is less than 13 seconds. So that would be the alternative right there. Okay, and that's our claim right there. Gives the null and alternative hypotheses. The null is greater than or equal. The equal part is always the null. So the level of significance is that 1%. And because n is 32, which is greater than or equal to 30, we're going to use the z-test. Okay, so here's our z-test. So it's going to be sample mean minus population mean divided by the the population standard deviation over the square root of your sample size. Okay, so crank all that out. We get about a negative 2.8. Okay, so what we do with that is we go look up on the table of z is negative 2.8, and we see there 0.0014. That's the area to the left of our z-score of negative 2.98. So that's our probability right there, 0.0014 right there, okay? Because that's less than 0.01, we can reject the null hypotheses, and of course interpret that. So there is enough evidence at the 1% level of significance to support the claim that the mean pit stop time is less than 13 seconds. All right, let's try another one. The National Institute of Diabetes and Digestive and Kidney Disease reports that the average cost of bariatric weight loss surgery is about $22,500. You think that this information is incorrect. You randomly select 30 bariatric surgery patients and find that the average cost for their surgeries is $21,545 with the standard deviation of, and I'm guessing that's a population standard deviation right there, of $3,015. Is that enough evidence to support our claim that it doesn't equal that? So doesn't equal means it's going to be a two-tailed one. So use a p-value. Okay, so the claim is the mean is different from 22,500. So your null, an alternative, your null is it equals 22,500, and your alternative is it doesn't equal, and that's our claim. Okay, so here we go. Our level of significance is at the 5% level, and so our sample size is 30, which is greater than or equal to 30. And we randomly selected it, so we can go ahead and use our z-score. So we plug in the information and we get about negative 1.73. Okay, so what we do is we go look up negative 1.73 on the z-score table, and that gives us just this area over here, 0.0418. Well, since it's not equal to, we got to include that area, so if we double that, we get 0.0836. So since that's greater than 5%, then we're going to fail to reject the null hypotheses. Okay, so interpret that. There is not enough evidence at the 5% level of significance to support the claim that the mean cost of bariatric surgery is different from 22,500. All right. Okay, and then for the TIs, you go to stats and choose test, and then check z-test. Okay, number 1 for a z-test. Okay, and then if you have data put in your list, then you would select data. Otherwise, when they give you the data, you know, like the sample mean and the standard deviation and all that stuff, then you hit stats on there. Okay, so here's an example right here. Let's plug in a sample mean of 6.07. The mean is 6.2 and the standard deviation is 0.47, and if we wanted to hit not equal to and then hit calculate, and it'll give us that right there. So the p-value would be 0.044046. So this look familiar? Okay, so for this test, it's 0.044. If our level of significance was at 0.05, then we could reject the null hypotheses. Okay. All right. So it did calculate it when it was not equal to. Okay. But if it was at 1%, then we would fail to reject because that's greater than 1%. So another method is to find the rejection region. Okay. So the rejection region or critical region is the range of values for which the null is not probable. So if a test statistic falls in this region, then the null is rejected. So the critical values of Z separates the rejection region from the non-rejection region. So guidelines for using the critical normal values, okay? So specify your level of significance, whether it's 10%, 5%, or 1%. Decide whether the test is a left tail, a right tail, or a two tail, and then find the critical Z values, okay? If the hypotheses test is a left tail, then find the z-score that corresponds to that area of either 5%, 10%, or 1%. Okay, so you look in the body. Okay, if it's a right tail, find the area that corresponds to 1 minus that, because remember the area in the body is always to the left of that number. So if it's a right tail, you got to do 1 minus that. That'll give you the area over there. If it's two tails, find the z-score that corresponds to half of your significance value, okay? And then 1 minus that will give you the right side right there, okay? So, and then sketch the standard normal distribution. Draw vertical lines at each critical value and shade that region for the rejection region. Now, if you can't find the exact area in Table 4, then find the closest z-score that gives you that exact area, okay? So find the critical value and rejection region for a left-tailed test with 1%, okay? So if we looked up 1% in the body right there, we'd find it, I think it was at 0.0099. I think we got a z-score of negative 2.33. Okay, so the rejection region would be any z-score that's to the left of that, okay? How about this one here? So find the critical rejection regions for a two-tailed test at 5%. Okay, so 5% means that both of them count for 5%. So this is half of 5% or 2.5%. So look up 0.025 and you'll see a z-score of negative 1.96. and look up 0.025, which is not 0.025, but this area is actually 1 minus 0.025, which is 0.975. So if we found a z-score at 0.975, that would give us positive 1.96. These guys are always opposites of each other, okay? All right, so the rejection region would be anything to the left of negative 1.96 or to the right of positive 1.96, okay? So here's some common critical values that I had my students write down. Hopefully they wrote them down somewhere in their calculator cover. Or maybe on the inside cover of their test booklet right there. Okay, those are the ones that pop up. Otherwise, you got to just look them up in the body. Okay, so if the standardized test statistics is in the rejection region, then that's enough evidence to reject it. If it's not, then we fail to reject it. Okay, so if it's a left tail and you get a z-score that's to the left of our rejection region right there, then we can reject it. Otherwise, we fail to reject it. If it's to the right of our z-score, then we can reject it. If it's to the left or to the right of our z-scores on a two-tail, then we can reject it. Okay, note, failing to reject your null hypotheses does not mean that you have accepted it as true. It just simply means that there's not enough evidence to reject the null hypotheses. Okay, all right, let's try this. So employees at a construction and mining company claim that the mean salary of the company's mechanical engineers is less than one of its competitors, which is $68,000. So a random sample of 30 people, that's greater than or equal to 30, and it says it's random, of the company's mechanical engineers has a mean salary of $66,900 with a standard deviation of $5,500. So at the 5% level, test the employee's claim. Okay, so the claim is the mean salary is less than that. So that would be my alternative, and that's our claim. And so the null would be greater than or equal to 68,000. Okay. All right, so because this tests a left tail, it's always our alternative. This is a left tail, so it's less than, so it's a left tail. And the level of significance is 5%, then we get negative 1.645 for our rejection region. So anything to the left of that or less than that would be rejected. So let's go ahead and do that. So here's our sample mean, here's our population mean, here's the standard deviation divided by the square root of 30. So if we plug that in, and we can use a z-score test because it's greater than or equal to 30. Okay, and I wasn't sure if that was the population standard deviation or the sample standard deviation, but we're going to pretend like we knew it was the population standard deviation, so that's what goes here. So when you crank that out, we should get about a negative 1.10. That is not to the left of that, that is to the right. So the graph shows the location. Because z is not in the rejection region, we're going to fail to reject the null hypothesis. So there's not enough evidence at the 5% level of significance to support the employee's claim that the mean salary is less than $68,000 at their company. All right, if you're in my class, you're going to get that for your assignment.